Okay, an example of how we spread and despread messages. If we go back to our system model, we have the message M of t, then we spread the message at the transmitter A of t, we have P of t coming out, then the channel, we add noise to P of t and also possibly other users. Then at the receiver, we receive a signal and we multiply that signal by A of t. So R of t equals message of t times A of t plus N of t. D of t is the received signal times A of t. If Y is our received signal, then we have the signature matrix X plus N. We'll just define the fact that N is the spreading gain in this case. So, and K is the number of users. So if we have a transmitted symbol, we have the first bit and we have K symbols being transmitted at the same time because there are K users. We multiply that by the signature matrix, which is of size N times K. So if we have a multi-user system model, we have Y, or the received signal, equals S, which is the signature matrix. That would either be the orthogonal or semi-orthogonal or random code. And we have X users and we're adding noise. Y, basically we have X bits transmitted at the same time and each uses a separate code. Y is an n by 1 matrix. X is a k by 1 matrix or a dimensional vector. And S is the signature matrix, which is n by k. N is the spreading gain, and k is the number of users. So if our original signal is user 1 is transmitting a 1, minus 1, 1, 1, 1, then that signal, so this bit here, would be spread n times. So we would say 1, minus 1, 1, 1, 1, minus 1. I'm making up these codes now. 1, 2, 3, 4, 5, 6, 7, 8. So that would represent what was transmitted for user 1. User 2, we would multiply minus 1 by the second code. 1, 2, 3, 4, 5, 6, 7, 8. And then I'll do the same for the other users. 1, 2, 3, 4, 5, 6, 7, 8. Up to the bottom one. So this is our X. Our S times X is a square matrix. Times X is a square matrix. Then we might not use, if this is 1, 2, 3, 1, 2, 3, 4, 5, I used only five users here, but we've got 1, 2, 3, 4, 5, 6, 7, 8. So in our case, the spreading gain is 8, and the number of users is 5. So S times X is A. So when we have a very large number of users, we've said there's not really a limit, but the capacity is reduced when we have a high interference. This is caused when the codes are not quite orthogonal or semi-orthogonal. I've explained why we can't always use orthogonal. The capacity is reduced by this L of Y. So when interference is very low, Y equals 0. So Ly is 0. So the capacity isn't affected because nothing is taken off. When interference is large, then we have infinity or heavy interference, then capacity is reduced by that amount. The symbol loading, or Y equals K divided by N, is a measure of the interference, so the number of users over the gain, and L of Y is the loss due to the presence of interference. So looking at the CDMA system model, we've talked about this a lot, but now we're going to see it in pictorial form. Here we have user X1, then it is transmitting a symbol, a 1, say, for instance. S1 is its code or signature matrix 1 that will be multiplied if it is 1s and minus 1s, or exclusively ORed if we're talking about 1s and 0s. The reason that we talk in 1s and 0s is because when we're implementing in hardware, we might be using logic. However, if when we're transmitting across the channel, we'll be transmitting different voltage levels, so we can't transmit 0 volts, so we use bipolar, so we use a 1 volt and a minus 1 volt. Sometimes 1 volt is represented by a 1 and minus 1 a 0. Sometimes we can have reverse, and 1 can represent a bit 0 bit, and minus 1 represents a 1 bit. As long as the transmitter and the receiver are both aware of what voltage level represents a 0 bit and what voltage level represents a 1 bit, then the signal should be received correctly. So here we multiply our signal, so rather than having just a 1, we have, let's say the spreading gain is 5, for instance, we would have 1 minus 1, 1 minus 1, 1, 1, 2, 3, 4, 5. So we'd be transmitting 5 bits rather than the single bit that we had. Then at the receiver, then we pass this to the channel. This is S, and we would add some noise. Then at the receiver, we would multiply our received signal, or Y, by the same S1, so by our 1 minus 1 before S1, and then we should recover X hat 1, or X hat should be equal to X1 if there is no noise and if the codes are orthogonal. Transmitter 2, we have X2, then transmitter 2 will be transmitting their value, and they will have a separate code, unique to S1, different, not unique. So then what we're passing to the channel is S1 times X1 and S2 times X2. We're adding them together, and then we're adding the noise. So Y is now composed of users 1 and user 2 data plus noise. And then at the receiver, if we multiply the code by the multiply Y by the respective code, then we should be able to recover X3. Now if we have a different code and that wasn't transmitting any message, then we should recover random noise until we have k users, or the kth user, and it has its own unique code. Then we show this as y equals sx plus n. So we represent this as a one-dimensional matrix, and S is a two-dimensional matrix. So if this is rows and columns, then this would be X, this would be S, and then we're adding noise to every single row and element in this matrix. I've drawn them as lines, these should be separate elements, and then at the output we multiply the received signal with the respective code, and we should get an estimation of what was transmitted. I'm going to go through an example in a minute. So here, in this case, if a 0 bit is represented by 1 volt and 1 bit is therefore represented by -1, then if we consider 3 users and 4 orthogonal spreading codes, you'll notice here that I've reproduced the Hadamard matrix for a 4x4 column matrix. So I've picked the first row to represent the spreading code for user 1, the second row to represent the spreading code for user 2, and the third code, or row 2, to represent the spreading code 3, and then we have a spare spreading code because we only have 3 users in this case. So if my input data is 0, 0, we've said here that a 0 bit is represented by 1 volt. So here I've put 0 bit is 1 volt, the second bit of user data is 0, and again that is represented by 1 volt. Here's our spread code. Similarly, if user data 2 is 1, 0, then a 1 is going to be represented by a -1 here, and a 0 again with a 1, and then this is user 2's spread code. User 3 is going to be transmitting 1 and 1, and their representation is a -1 volt and -1 volt, and their spread code is given here. So because we're using 1s and -1s, we can just simply do a modulo 2 multiplication. If we kept it in terms of 0s and 1s, then we would just do an exclusive OR operation. And I've showed why we use 1s and 0s, because the shift registers use 1s and 0s. So, data from user 1. We're transmitting 1. So we have this first data bit, and then we're going to multiply it by the 4 bits. In our case, in this case, our G equals 4 and our K equals 3. So we've got K users and our spreading gain is 4. So for the first bit, we transmit 1, 1, 1, 1, because it's 1 times 1, 1 times 1, 1 times 1, and 1 times 1. For the second bit, then we repeat the same code that we already had, the 1, 1, 1, 1, with the second bit of data. So again, we transmit 1, 1, 1, 1. We do the same thing for the second user. So here we're transmitting a -1, and we copy the code down, 1, -1, 1, -1, to code 2 here, and then we multiply out -1 times 1, which is -1. -1 times -1 is +1. -1 times 1 is -1. -1 times -1 is 1. So that's the first bit encoded or spreaded. Then the second bit is a 1, and we copy this code 1, -1, 1, -1 again. So 1 times 1 is 1, 1 minus 1 is -1, 1, 1 is 1, 1 minus 1 is -1. So this is the spreaded message too. In a spread the message 3 and we would get the following code as shown here. Okay, so this is our S1, X1, X plus X2, X2 plus X3, S3, or S3, X3. So now what we need to do is add them together or combine them to make the composite. So if I draw this in terms of voltage waveforms, so I've used this representation here. 1 is here, 0, it's at the bottom of the cell, -1 is represented by the bottom line. So user spread data is all the ones. User 2 spread data is this waveform as shown here. So -1, 1, -1, 1, 1, -1, 1, -1. User 3 data is -1, -1, -1, plus 1, plus 1, -1, -1, plus 1, plus 1. So the composite waveform is the addition of these three at the different instances in time. So it will be the addition of these 3 bits, then the addition of these 3 bits, and the addition of the following 3 bits. So we have 1 minus 1, which is 0, minus 1, which gives us -1. That's for the first bit. The second bit is 1 plus 1, which is 2, minus 1, which gives us 1. Then we've got 1 minus 1 plus 1, which gives us 1. Then we have 1 plus 1 plus 1, which gives us 3. 1 plus 1 is 2, minus 1 is 1. 1 minus 1 is 0, minus 1 is -1. And 1 plus 1 is 2, plus 1 is 3. 1 minus 1, 0, plus 1 is 1. So the composite waveform is shown here. And I've written it as -1, 1, 1, 3, 1, -1, 3, and 1. Okay, so I've copied what was transmitted here. And then composite waveform is our Y from our previous example. In this case, we've assumed noise equal to 0, or a signal to noise ratio. If noise is equal to 0, signal power of a 0 divided by a 0 noise power, so it's an infinite signal to noise ratio. SNR tends to infinity when noise equals 0, because it's signal power over noise power. Okay, so if we are in receipt of Y and we have, say, spread code 1, so we're in possession with this spread code and we know it's in synchronization with what was transmitted. So what we do is we multiply our spread code with the composite waveform. So we have -1 times 1 is -1. 1 times 1 is obviously 1. Because we're multiplying everything by 1, we essentially have our spreaded code, or composite motion times spread code, is equal to the composite waveform. So -1, 1, 1, 3, 1, -1, 3, and 1. Now, if we sum the resultant up, so that we get -1 plus 1 plus 1 plus 3, we get 4. Then we divide it by the chip rate, or the spread code, which is, or the gain. This is also equal to the gain. So 4 over 4 gives us 1. And we said a 1 represented 0. So 1 represents a 0 here. And hence a 0 was actually transmitted. Same thing again for the second bit. 1 minus 1. 1 minus 1 is 0. Plus 3 is 3. Plus 1 is 4. 4 over 4 is a 1. 1 equates to a 0. And 0 was in fact transmitted. So we've recovered the user 1 data successfully. Well done. So if we're in possession of spreading code 2 and we receive the composite waveform Y, then we obviously do the same procedure again. So 1 times minus 1 is minus 1. Minus 1 times 1 is minus 1. 1 times 1 is 1. Minus 1 times 3 is minus 3. 1 times 1 is 1. Minus 1 times minus 1 is plus 1. 1 times 3 is 3. And minus 1 times 1 is minus 1. So then we have minus 1, which is minus 2, plus 1, which is minus 1, minus 3 gives us minus 4, minus 4 over the spreading gain, 4 is minus 1. Minus 1 represents a bit 1, so the transmitted data is 1, and it was in fact 1. We do the same thing with the second bit. 1 plus 1 plus 3 is 5, take away 1 is 4, 4 over 4 is 1, and 0 was transmitted. So we'll spread code 3, and I'll leave you to do that, but I hope you will confirm that 1 and 1 was transmitted. Now the final question is we didn't actually transmit any using the spare spreading code. Now what happens if I multiply this spare spreading code by the composite waveform? Actually what we get is zeros out. So minus 1 minus 1 minus 1 is minus 3, and then we get plus 3 there is 0. So in each case we get zeros out, so nothing was transmitted. The reason we get 0 here is because we used the Hadamard or the orthogonal codes, and also no data was added. No noise was added. If there was some noise, or if they were semi-orthogonal or random, then we would get some small random noise appearing here. However, we would still not be able to determine whether a 0 or a 1 was transmitted, and that doesn't actually matter. But basically what I'm saying is if you're not in possession of a valid code, then you're not able to decode what was transmitted. That's the main point of what I'm saying. Okay, as I've already mentioned, it will already work for opposite voltages as long as the transmitter and the receiver have the same voltages. And also if we used exclusive OR, if we didn't convert to voltages, we just use ones and zeros, we could use the exclusive OR to do the spreading operation. XOR is easier to implement in hardware using logic gates. However, when we're transmitting BPSK or QPSK, then we need voltage levels.